Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Baswakaland. Today, in the 36th session of Graph Theory 2, we are discussing some problems related to chromatic numbers. So, we consider some problems and we try to find the chromatic number of those problems. So now we consider two theorems first. So the first theorem is, if H is a subgraph of a graph G, then the chromatic number of G is greater than or equal to H. So we are considering a graph G and H is a subgraph of the graph G. The theorem or the statement of the theorem is, if H is a subgraph of a graph G, then the chromatic number of G is always greater than or equal to the chromatic number of the subgraph H. Okay. So to prove this result, what we will do, first we consider the chromatic number of a graph is K. Let us consider the chromatic number of the graph G is K. And let F be a K coloring of G. You know already what you mean by K coloring. Means the graph is colored with K colors. Then it is called K coloring. So let F be a K coloring of G. Then F restricted to the vertex set of H, or you can say the vertex set of the subgraph H, is a K coloring of H. So we can conclude that the chromatic number of the subgraph H is always less than or equal to K, where K is the chromatic number of G. So this theorem leads to one consequences. So an important consequences is the following corollary. So if G contains a complete subgraph Kn, so if any graph contains a complete subgraph Kn, then the chromatic number of that graph is always greater than or equal to n. For example, if you consider a graph G, in that if there is a complete graph K3 as a subgraph, so if it is K3, then the chromatic number of that graph is always greater than or equal to 3. If K4 is the subgraph of G, then definitely the chromatic number of such a graph is greater than or equal to 4. So in general, if G contains a complete subgraph Kn as a subgraph of the graph G, then the chromatic number of that graph is always greater than or equal to n. Okay, so this is a simple corollary based on the previous theorem. Now we are considering another theorem. Suppose if G is a PQ graph, means G is a graph with P number of vertices and Q number of edges, then the chromatic number of that graph is always greater than or equal to P square divided by P square minus 2Q. So the chromatic number of a graph with P vertices and K edges, Q edges, is always greater than or equal to P square divided by P square minus 2Q. So what you can say, is it an upper bound or lower bound? So chromatic number is always greater than or equal to this. It implies it is the lower bound. Okay. So therefore, we try to prove the theorem. First, we consider chromatic number of a graph is K. Suppose the chromatic number of a graph is K. By the previous theorem, there is a partition of the vertex set V into the disjoint subsets, say V1, V2 and so on and so forth, Vk. Okay. So that is the color class, what we can say, the color class. So we are partitioning the vertex set into the subsets V1, V2, V3 and so on and so forth, Vk. And if you find the union of all the subsets of the vertices, or definitely it will be a vertex set of the graph G, such that no two vertices in Vi are adjacent. It's very obvious that no two vertices in Vi are adjacent. So because the color class, in a color class, we are considering the vertices of the same color. So that's why V1 is a partition of the vertex set having the vertices of the same color. Similarly, V2 with another color. So like that. So these are the subsets V1, V2, V3 and so on and so forth, Vk. Obviously, if you find the union of all these subsets, definitely it will be a vertex set of the graph G. Okay, so let the number of vertices in the subset Vi is equal to Pi. So where I lies between 1 and k. So you can say 1 is less than or equal to k is less than or equal to, sorry, 1 is less than or equal to I is less than or equal to k. Then Qg, that is the number of edges in a graph. So it is PC2 minus summation Pi2, that is the summation of the combination PIC2. Okay, so already we know the result 2Q is always less than or equal to P square minus P minus sum of the squares of the vertices, that is Pi square, plus summation Pi where I equal to 1 to k. That is you can say it is P square minus summation Pi square where I equal to 1 to k. Since sum of Pi's, that is the vertices P1, P2, P3, if you find out the union, or you can say if you add the number of vertices, definitely it will be the number of vertices as that of the graph G, P. Okay, so which is less than or equal to P square minus, so summation Pi where I equal to 1 to k square, that is the square of the summation of Pi over k. So we got this result since we have got one Cauchy's-Schwarz inequality. So that is summation Pi square is always greater than or equal to summation Pi square divided by k. So which is equal to P square minus P square divided by k. So hence you can conclude k is always greater than or equal to P square minus 2q. Okay, so this is how so this is the result, and we are doing the result in this way. Okay, so I think so now you got this picture. So therefore once again let me recall, so k is greater than or equal to P square divided by P square minus 2q. So in this way we can conclude the result of the theorem. So what is that? If G is a PQ graph, then the chromatic number of that graph is always greater than or equal to P square divided by P square minus 2q. So in this way we have proved the result. Now we try to consider some examples based on the chromatic number of some graphs. Let me consider some examples. Suppose if I ask you to find out the chromatic number of the following graph, it is just k4 minus x, we can say. K4, it is a complete graph with 4 vertices and one edge is deleted from that. So it is like k4 minus x. So what would be the chromatic number of this graph? So first what you have to do, try to start the coloring of a graph. You can start with any vertex, arbitrary vertex. You can choose any vertex of your choice and try to start the coloring of the vertices in such a way that the adjacent vertices must have different colors. Okay, so we just start with the vertex by coloring 1 or by assigning the color 1. Then if you come to this vertex, these two are adjacent vertices, so that's why I have colored with a 2. Now if you consider this vertex, here it is adjacent with both the vertices which are assigned with the color 1 and 2. So you cannot assign 1, even you cannot assign 2. So that's why we have to assign the color 3 for this vertex. Now for this vertex you cannot assign 1, you cannot assign 3, but you can assign 2 because it is not adjacent with the vertex which is colored with 2. So you can color with 2. So this is how we have colored the graph, and these are the minimum number of colors we have used. So what would be the chromatic number? Here we have used 3 colors, so therefore the chromatic number of this graph is 3. So let me consider another example. Find the chromatic number of the following graph. we have considered another graph. Again, in the same fashion how we did in the previous example, you start coloring with any arbitrary vertex. Say for example, I have started the coloring of a graph with this vertex. So just assign the color 1 to this vertex. Then if you consider this vertex, you cannot assign by 1 because it is adjacent with the vertex colored by 1. So therefore you have to use another color, say color 2. Now if you consider this vertex which is adjacent with both the vertices, so therefore it is not possible to assign the color 1 as well as 2. You have to assign the color 3. In this way, if you consider this vertex, so you cannot assign 3, but you may assign 1 or you may assign 2. So for example, we have assigned, okay, first take this vertex. So you cannot assign 3, but you can assign 1 as well as 2. So better consider 1. Okay, so now if you consider this vertex is adjacent with the two vertices colored by the color 1 as well as color 3. So you cannot use the color 1 as well as color 3. You have to use the color, another color, the previous color which you have used, 2. So in this way, if you color the graph by minimizing the number of colors so that the adjacent vertices are colored with the different colors, then the chromatic number of this graph is 3. Okay, so let us consider another example. So find the chromatic number of the following graph. Okay, so this is one graph which contains 3 blocks, you can say. Okay, again in the same fashion you try to start the coloring of a graph with any of the vertices. So again in the same fashion, this vertex with a 1, then this vertex with a 2. So you cannot assign 1 and 2, so you have to assign another color, say 3. So like this, again if you come for this vertex, it is 1. For this you can use 2. So for this vertex you can use 1. For this you cannot use 1 and 2. You can use the color 3. So for this vertex you cannot assign 1 as well as 3, but you can assign the color 2. Again this graph is 3 chromatic because the chromatic number of this graph is 3. So this is how we took some examples to clarify the chromatic number of a graph. So consider one more example, that is the fourth example. Find the chromatic number of the following graph. Okay, so this is the graph. Again start with this vertex 1 by assigning the color 1. If you consider this vertex which is adjacent with the previous vertex colored by 1, so you have to assign the color 2. So this is how we have colored with 1 as well as 2. If you consider this vertex which is adjacent with the vertex colored by 2, you cannot assign the color 2, but you can assign the color 1 because these two are non-adjacent. So you can assign the color 1. So this is how, if you use the color 2 for this vertex, the adjacent vertices must be colored with 1. Again, this vertex is adjacent with both the vertices with the color 1. You can use the color 2 because these two are non-adjacent. So this is how we have colored, and we took only 2 colors to color the entire graph. So therefore the chromatic number of this graph is 2. So you have to observe, we took 3-4 examples. What's the difference? You just concentrate on the cycle, whether it is a cycle with odd length or whether it is a cycle with even length. That is very important. Okay, so overall in this session what we have discussed, in this session we have discussed some problems on the chromatic number. Even we have considered 1 or 2 theorems, some useful theorems, and based on those theorems also we have considered some examples to find the chromatic number of such graphs. Okay, so these are the reference books. If you want, you can refer any of the books. Already in the previous class also I have mentioned. So with this we conclude this session. Okay, I hope you have understood all the ideas properly. So with this we conclude this session. Thank you.